Today we're at the Owens Valley Radio Observatory and we're going to talk about the Drake equation. Today we're going to discuss the Drake equation. The Drake equation was developed by Dr. Frank Drake at the Green Bank Radio Observatory in Green Bank, West Virginia, the nation's only quiet zone. What's the Drake equation? I don't know what the Drake equation is. Is that a singer? Is that like a formula he uses to drop the beats? No, not. That's the wrong Drake. We're talking about Frank Drake, Dr. Frank Drake. The purpose of the Drake equation was for the search for extraterrestrial intelligence. It was a mathematical formula that was designed to try to put together some number of how many alien civilizations that have technology could be in the universe. Well, that was a tall order. How would you even go about that? I mean, Drake came up with this in 1961. The Drake equation has been foundational and has been in use since 1961 in trying to get a handle on what's out there. And every time we make another discovery, we have to go back to the Drake equation and change all of our variables because we know more. It was since the Voyager tour of the outer solar system, the discovery of water ice throughout our solar system, the Kepler telescope missions, finding extrasolar planets. All of that knowledge we have to go back and readdress the Drake equation to try to come up with another number of intelligent species in the universe. So let's go over it. The Drake equation, I'll put this up on the screen. Drake equation starts with N. N is the number of civilizations. So here's exactly what N equals. It is the number of civilizations in our galaxy with which communication might be possible, i.e., which are on our current past light cone. In other words, which ones can we listen to? Which ones can we see? Which ones are aimed our way? And it's a series of variables all multiplied together that gives you the N number. R is the average rate of star formation in our galaxy. How fast are we? Oops. I can't hold my pants up to save my life. I lost a bunch of weight. Let me pull my pants up again. Jesus, this is embarrassing. So let's read down the variables. R is the average rate of star formation in our galaxy. Now that's the rate of which stars are formed. And they have a long, stars have a very long life, usually in the billions of years. So it's not like they're popping up every day, but they kind of might be. Now that we have more information about star formation, they could be popping up a lot. So R is the rate of star formation in our galaxy. The next one, F of P, the fraction of those stars that have planets. Well, with the Kepler data that's been coming in, my God, there's planets everywhere. It's like, stars are so greedy. Oh, I just have to have me a planet. I want me some planets. You've got plenty of planets. I want some too. I want some big ones. Oh, I want the big Jovian monsters. Planets are everywhere. So our number starts to tick up. The next variable is N of E, the average number of planets that can potentially support life per star that has planets. Again, Kepler was actually good money spent. A lot of these stars have planets that we think are in the Goldilocks zone, where you have a temperate climate, maybe the inclusion of water on the planet. It's not too hostile, either too cold or too hot. But here comes the but for this one. We've discovered so many life forms on planet Earth, we call them extremophiles, that live in volcanic vents under the sea, where we didn't think nothing could live. It's too, the temperature is way past boiling, the pressures are extreme, you know, it's too far down for even somebody in a scuba suit to go. Very few submarines are built to withstand this pressure. And here we got crabs, shrimp, all flying around, you know, different types of anemones, all surrounding these hyperthermic vents, rich in sulfur, high in pressure, really high in pressure, and high in temperature. So our Goldilocks zone looks to be maybe a little bit bigger. And then we have things like tardigrades. Tardigrades ruin the bell curve. Let me tell you, they can live in space, the vacuum of space. They can be frozen for hundreds of thousands of years. They can be boiled, they can be fried, and they still live. Tardigrades have survived just about every planetary calamity Earth has gone through. And they're still here. So again, we have to expand the Goldilocks zone. I mean, originally the Goldilocks zone was for us. You know, maybe our beagle, pet cat, the goldfish. But if you look at all the things that are alive on Earth right at this second, the Goldilocks zone is large. I mean, it's really big. I swear, there should just be a conference every year, and there probably is, to redo the Drake equation. The next variable in Drake's equation is f of L, the fraction of planets that could support life, that actually develop life at some point. Okay, we're fuzzy on this. We have a lot of theories. You know, we can look at what the Goldilocks zone is for Earth and all the extremophiles and kind of extrapolate what planets might be able to support life. There's lots of places in the solar system we could go to help us define that. Mars, of course, Enceladus. There's a bunch of places. I mean, if we have extremophiles that thrive in hot, boiling sulfur water, then maybe Io? I don't know. We just don't know. So that number could be potentially huge. But we don't have any data for it yet. Like the others, we have some data and we can make guesses, but now we just got the extremophiles we have here on Earth as an example, and we have to extrapolate to what we think these extraterrestrial planets may be made of. The environment, like a lot of things in the Drake equation, is kind of a gray area. But we can make, you know, responsible assumptions and go with that. Here's another one. We're really narrowing it down now. F of I, the fraction of planets with life that actually go on to develop intelligent life. Civilizations. Well, you know, humans certainly have civilization. I mean, if you've probably seen some of my petroglyph videos, certainly civilization chiseled those petroglyphs into the volcanic rock here in Southern California, as they've done all across the world. We've built monumental structures, we've built pyramids, we've built these things. It only took us 66 years to go from Kitty Hawk to the Sea of Tranquility on the moon. That's amazing. Our civilization in terms of technology has risen very quickly, very quickly. I mean, just looking at some of our older writing, I mean, the petroglyphs farther up this valley, they're 8,000 years old, 3,000 years old. I mean, that is just a blink in time compared to how old the universe is. Next up is F of C, the fraction of civilizations that develop a technology that releases detectable signs of their existence into space. We're talking about radio. We're talking about radio waves, and if you really want to get advanced, you know, maybe later on, lased light. But the whole thing behind radio astronomy is listening to the sounds of the universe. I mean, you can see the visual light coming down and bouncing off me and entering to the camera lens. But there's so much more in the radio spectrum that we cannot hear, that we cannot see, that's at really high frequency ranges, that it takes instruments like this just to receive them. And some of our early broadcasts from the 30s and 40s made it out into space. And they're traveling at the speed of light. So somewhere there's an old Andy Griffith show. Somewhere Lassie, is trying to rescue Timmy from the well. Somewhere out there is Walter Cronkite announcing the last helicopter out of Saigon. It's still traveling. It's still out there, pushing forward into the universe. And that's what the whole SETI program is about, listening for someone else's broadcast. And then there's L. L is the length of time for which such civilizations release detectable signals into space. That's a big one. When I was growing up, AM radio stations, FM radio stations, television stations, we were broadcasting stuff all over the planet to each other. And a lot of those signals were powerful enough and high enough frequency that they escaped Earth's magnetic field and continued on into space. We still have powerful radio transmissions going up to satellites in geosynchronous orbit, coming back down from geosynchronous orbit. How many of you at home have an aerial antenna on your house to get TV? I haven't had one of those since 1984. Since then, it's been cable. And now with cell phones at very high frequencies and very low power, my cell phone doesn't escape Earth's gravity. The antennas designed for it are all kind of flat. They want to maintain the signal close to the Earth, so everything's projected outward, not upward. They don't want to waste that energy, that radio energy. So are we actually, and I don't know the answer to this, hopefully someone can drop that in the comments, but are we actually putting out more signals now from Earth that we did back in the 50s, 60s, and 70s? Or is Earth quieter now than it was 50 years ago, 40 years ago? I know now the big microwave antenna towers, those are gone. Those big antennas are gone. Hardly anyone uses them anymore. So I don't know the answer to that. But my feeling is we're getting quieter, because the big antennas, those pushing out the most signal, seem to be dying off, falling into disuse as we now use the internet for just about all of our communication needs, planetary communication needs. A little cell phone, you can talk to anybody on planet Earth that's got one. And you don't need a big, huge amplifier to do it. So we may be becoming a quiet species. Maybe our L was 50 years. Maybe our L was 60 years. I can't see it being 600 in the future. Is there such thing as entangled radio? Would we use that for deep space missions? We've got one data point. Us. That is our baseline. Humanity is the baseline for L. And we may be on the decline concerning total irradiated electromagnetic energy going out into space. So our L may be remarkably short. I just don't know. But please, if you know, drop that in the comments below. I'll do a follow-up if you do. If I can find out, I'll do a follow-up. So that's it here from the Owens Valley Radio Observatory. If you like this video, please give it a thumbs up. If you like what I'm doing on the channel, please subscribe. Yeah, subscribe. If you got any questions, drop those in the comments below. Please check out SciWorx on my Patreon channel. Links below. Until next time, I'll be your lab partner. Take care. Goodbye.